This video finishes up Chapter 9 on alkynes. This video will discuss the reduction of alkynes, the oxidative cleavage of alkynes, alkyne acidity, alkylation of acetylide ions, and an introduction to organic synthesis. Alkynes can be reduced. Now, reduction means the addition of hydrogen or the loss of oxygen. So here we can take an alkyne to the corresponding alkane by adding hydrogen and a catalyst. The first addition produces a cis-alkene via syn addition, like we saw with the alkene hydrogenation, but then that is also reactive towards hydrogenation, so that will react a second time to produce your alkane product. Now you can actually stop the reduction at the alkene stage a couple of ways. The first is to use H2 with a poisoned catalyst. So a poisoned catalyst, such as Lindlar's catalyst, prevents the second reaction from happening at any appreciable rate. And importantly, you always are going to get a cis-alkene when you use H2 and a poisoned catalyst such as Lindlar's catalyst. And Lindlar's catalyst is a combination of all of these reagents: quinoline, palladium, barium sulfate, and methanol. The way Lindlar's catalyst works is it facilitates the first reduction to the cis-alkene, but then it doesn't catalyze the second step. So if you are monitoring your reaction, once the alkene is formed, you can stop the reaction and isolate it. The second way to produce an alkene is to use a dissolving metal reduction. Typically, lithium or sodium is used in an ammonia solvent, and this will always give you the trans-alkene product. So here we see a series where we start with 4-octyne, and with H2 and Lindlar's we get the cis-octene product, but then we could further react that if we wanted by using H2 on palladium on carbon or some other similarly active catalyst to produce the alkane. And then here is an example. If we started with this 5-decyne and we used lithium and ammonia, we would stop at the alkene, and in particular we would get the trans-alkene. This is the mechanism for the lithium or sodium and ammonia reduction to give the trans-alkyne. First, the lithium metal donates an electron to the alkyne, which gives this vinyl radical, and then that negatively charged carbon grabs a hydrogen from ammonia, and then the vinyl radical accepts another electron from a second lithium atom to produce another vinylic anion, which then gets protonated again from ammonia. So two steps which are identical but happen in sequence. And then as a result, you get the trans-alkene product. You can also perform oxidative cleavage of alkynes. It's actually a little bit simpler than what we saw with alkenes, because no matter what you use, ozone or KMNO4, you always get carboxylic acids for internal alkynes, or if you have a terminal alkyne where one of the carbons is attached to a hydrogen, you get a carboxylic acid plus CO2. So this carbon becomes the carbon of CO2. This carbon is the carbon of the carboxylic acid. And here, this carbon would be that carbon of that carboxylic acid, and this carbon is that carbon of the second carboxylic acid. So again, we're chopping right down the center of the triple bond and then converting those functional groups into oxidized functional groups. Terminal alkynes, again, that's an alkyne where one of the carbons is bonded to an H, are acidic, and they can be deprotonated with a very strong base, such as sodium amide, shown here. And that gives you what's called the acetylide anion. So when the triple bond is deprotonated, we call that an acetylide anion. Now, acetylene has a pKa of 25. Remember, the lower the pKa, the stronger the acid. So that's a stronger acid than ethylene. In fact, it's 19 pKa units more acidic than ethylene. And that is 6 pKa units more acidic than ethane. So notice the trend here. So because it's acidic, we can use a base which would deprotonate that hydrogen and leave behind those 2 electrons on the carbon. Now the reason that the acetylene is more acidic is because its conjugate base is more stable compared to the ethylene and the ethane. And the reason for that is the type of orbital that lone pair resides in. So with a triple bond, that lone pair is going to be in an sp orbital. With ethylene, it would be in an sp2, and with an alkane, it would be in an sp3. The more s character that an orbital has, the more tightly the electrons in that orbital are held to the nucleus. In the case of a negative charge, that provides stability. So the negative charge of the acetylide is stabilized by the fact that that lone pair of electrons is held in an sp orbital closer to the nucleus, because the positive charge of the nucleus wants to be close to the negative charge. So sodium amide, NaNH2, is often used as the base, but others can also be used as well. So whenever we're looking at our acid-base equilibrium to figure out if a base is strong enough to deprotonate something, we would compare the pKa of the starting acid and the conjugate acid. So if the conjugate acid is weaker than the starting acid, then the equilibrium would favor the products. So here we have acetylene, and all of the acids above it, these are weaker than it because they have higher pKa values. So the corresponding bases that they came from would be strong enough to deprotonate acetylene. However, these bases will not deprotonate a terminal alkyne to any appreciable extent because the conjugate acids that they make are actually stronger than acetylene. So remember, in an acid-base equilibrium, the equilibrium favors the side with the weaker acid. So if we used these in the acid-base equilibrium, the product acid would be stronger than the starting acid, so the equilibrium would not favor products. Now we can use those acetylide ions and we can actually react them with alkyl halides to produce a new product. So here the acetylide ion, that negatively charged carbon, will attack this carbon, kicking off bromide. And this is an example of an SN2 reaction that we're going to discuss in great detail before Thanksgiving break. And then as a result, we've created a new carbon-carbon bond right here. So this is a preview of SN2 reactions that I would like you to know for this chapter. So this is the mechanism. The negatively charged carbon attacks the carbon of the alkyl halide, kicking off the bromide at the same time. This is a picture of the transition state showing the bond forming and the bond breaking at the same time. And then this is the product shown here. So reactions, if we have a terminal alkyne, we can first deprotonate it with something like sodium amide, NaNH2, in liquid ammonia solvent. And then that creates the acetylide, which then react with an alkyl halide, will alkylate the acetylide. So this portion of the molecule came from step 2, that butyl bromide. So in a generic fashion, what's happening is we have a terminal alkyne, which we're deprotonating with this strong base, and then it's attacking the alkyl halide and attaching that additional portion to the alkyne. The final topic is organic synthesis. So organic synthesis is vital to the pharmaceutical industry, chemical industries, and academic laboratories. Indeed, my expertise is in multi-step organic synthesis. And planning a successful sequence involves having your knowledge of chemical reactions, so knowing all the different transformations and the reagents that they require, and then organizing that into a plan. And oftentimes we have a target that we want to make, and so we want to figure out how we can make that target compound from simpler compounds. And to do that, we often work backwards in what's called a retrosynthetic direction. In general, it's called retrosynthesis. And we're going to do some problems in class as well applying this technique. So for example, I might say prepare cis-2-butene, this should be butene, using propyne and alkyl halide and any other reagents needed. So this would be the final product. So how could you get to that from something else? Well, that would be the H2 reduction product if you were using Lindlar's catalyst that you would make from this alkyne. And then you could get to that alkyne from a simpler alkyne, a terminal alkyne, upon treatment with a strong base and methyl bromide. And is this the only possibility of how to make this? No, but this involves reactions that you've just learned. Now test your understanding with these next questions. First of all, what is the name of the product of this reaction? So not the name of the reaction, but the name of the product that you make. So you're starting with a terminal alkyne, you're adding sodium amide, which is a strong base, and then you're adding a 3-carbon alkyl bromide. So what will you get when you do that? The next few are going to look at the different types of reductions with alkynes. So for this one, if you use hydrogen with platinum, what would your product be? Would you get an alkane or would you get an alkene? Again, here's another reduction, but this time we're using sodium in liquid ammonia. You could also use lithium metal here. What type of product would you get here? Finally, what if we reduce this with H2, but instead of using palladium or platinum, we're going to use the special Lindlar's catalyst, which is a poisoned catalyst? What type of product do you get here? Now this question is asking you to pick the reagent. So I'm giving you the starting material and the product. Can you identify what type of reagent works to give you a trans alkene? And your final question, what starting material would produce these fragments after treatment with KMNO4 or ozone? And it will be helpful to number your carbons, 1, 2, 3, 4, and then you also have a CO2 fragment. So would that come from cleavage of A, B, C, or D? Put your answer in the chat.